to the South Pole, and it basically doubles the cost. So that's the current state. There's quite as much.
Welcome everyone. We just heard an excellent ITC colloquium by Eli Waxman. He would tell us more about the specific astrophysical environment very soon. I just wanted to mention Eli has a long history of important contributions in related to high energy cosmic rays. That was early at the time that we had a little bit of overlap at Princeton. And then he went on to develop a much deeper understanding of gamma ray bursts and their afterglows, neutrinos emitted by various sources, and most recently, I guess it's a sign of aging that he became an observer, an experimentalist, I would say, designing a new mission that he described that will cost $100 million and will get very interesting science in the UV about transients. That's what he described in his lecture. The other thing I wanted to mention before we get to the list of speakers is that the Nobel Prize was awarded this week, as many of you know, in physics and chemistry. And there are two important lessons that I learned, which are quite interesting. The first is that artificial intelligence for the first time was rewarded, and both in the context of physics and chemistry. Why is that interesting? Well, an hour after the chemistry award was announced, I was on Zoom with one of the members of the Nobel committee, and my question was, you know, that in the near future it's quite conceivable. I mean, right now AI is helping science, but within a decade or two, the discoveries may be made by AI, and the humans will just be managers of those systems. And the question is, will the Nobel Committee give credit to the AI system and give the prize to a non-human machine? And his answer was no, because according to the rules of the Nobel Prize, you can only give the prize to humans. Okay, so that was his answer. So that's one interesting development, that now AI is recognized at the frontiers of science. And the second thing that I noticed was three of the people who got it were associated with Google. And that's an interesting development because, you know, usually we think of the commercial sector as being less blue sky, more application-oriented, and universities are celebrating blue sky research. It's not the case anymore. The corporations do have more money than universities to invest in innovative technologies and breakthroughs in science. And we see that this year with 3 Nobel laureates associated with Google. That's a new development. So just, I think it's an opening of a new future where science will be done both in the private sector as much as in universities and be celebrated. And the second is that AI will be an important part of that. So these are just general comments. And so other than Eli, we'll hear from Keiya Hirashima from the University of Tokyo. Where is he? Over there. He will talk about the AI surrogate modeling for supernova feedback towards star-by-star galaxy simulations. So this is using AI on simulations, so everything is in the virtual world. And then we'll hear from Yijia Lee from Penn State. Where is Yijia? Oh, here she is. And she will tell us about Q, a fast and flexible emulator for modeling nebular emission. And finally, from Michelle Brann here at the CFA, Methyl, Cyanide, Interstellar Ice, Analog Photochemistry. So this title is just a noun, actually, right? We will hear more about it. Eli, please go ahead.
Okay, so I'll talk a little bit about hydrogen neutrinos.
Is there a microphone? Do you have a microphone?
There is a microphone, but don't you hear me
because
well?
we cannot hear you in the back.
This is the sign of your aging.
Someone more?
No, it's better? Okay. Okay, so I'll say a few words about high-energy neutrinos. As you probably know, IceCube, the neutrino detector in the South Pole, detected extraterrestrial high-energy neutrinos. And the main things that we have learned are summarized in this slide. You can see the IceCube measurements, flux as intensity as a function of energy. So we have this extraterrestrial signal above a few tens of TeV. The measurement of the intensity enables us to determine the rate at which high-energy neutrinos are produced in the universe, rate per unit time and volume. And since the intensity is similar to our upper bound on the intensity that could be produced by cosmic ray energy loss, this implies that the energy production rate of the neutrinos and the cosmic rays are similar, and it's about 10 to the 44 ergs per cubic megaparsec per year. The sources have not yet been identified. We don't know what the sources are. One of the goals is to identify the sources of the cosmic rays, but what we know now is only that since we do not observe multiple events from a single direction, from a single source, we only have a lower limit on the number density of sources and an upper limit to their individual luminosity. So they should be not extremely bright. So the typical luminosities are less than 10 to 42 ergs per second, which is, say, ruling out classes of sources which are extremely bright, like blazars and other rare objects. Now, what I would like to focus on in these few minutes is actually on the lower part of the spectrum. At an energy between 10 to 30 TeV, the flux is about twice the bound, and the intensity puts this in some tension with the gamma ray background measurements. So high energy neutrino production by cosmic ray energy loss to pion production is accompanied by high energy photon production, and these high energy photons, after interacting with the infrared background, emerge below 0.1 TeV and produce a gamma ray intensity which is similar to the neutrino intensity that we observe, and which is in tension with the observed Fermi gamma ray background. So this had led to increased or renewed interest in gamma ray hidden sources that produce neutrinos but do not allow gamma rays to escape in order to avoid the tension with the gamma ray background. And I would like to discuss a possible source that can do this. Supernova shockwaves. So the shockwaves that supernova drive into the interstellar medium or circumstellar medium are presumably cosmic ray sources. And the interaction of these cosmic rays with the interstellar gas would produce pions that would produce neutrinos, almost unavoidable. However, the typical densities of the circumstellar medium around the progenitors of supernova stars are low, and the neutrino luminosities that would be produced is quite low, cannot be a significant contributor to the 10 TeV neutrino background that was measured. However, we have pointed out a way back that if the progenitor star is surrounded by some dense optically thick circumstellar medium, the neutrino luminosity could be increased by orders of magnitude. At the time when we proposed it, we were thinking of some rare X-ray flashes associated with compact progenitor supernovae. However, and these are quite rare objects, so they will not contribute much to the background. However, recently we have growing evidence that the prevalence for the prevalence of optically thick compact CSM shells around supernova progenitors. We have different observational lines of evidence. One, most type 2N supernovae, those that show narrow lines indicative of interaction with circumstellar medium, show precursor emission, 10 to the 47 erg tip or larger bursts during the year preceding the supernova explosion. Now, depositing such amount of an energy in the envelope of a supergiant would lead to the ejection of a fraction of a solar mass of the envelope to a distance of 10 to the 14, 10 to the 15 centimeters in a year. A survey of early detection of regular type 2 supernovae with ZTF and early UV follow-up by SWIFT showed that half of these supernova, the early light curves, are consistent with just the expanding cooling envelope of the shocked envelope star. However, half of them show a fairly slow day-long rise to a few times 10 to the 43 ergs per second UV luminosity. And this is most naturally explained as due to the supernova shockwave driven into the circumstellar medium, leading to this strong UV emission. And again, from the duration of this rise of a day time scale, we conclude that the extent is a few times 10 to the 14 centimeters, given that the supernova shock wave is at 10,000 kilometers per second. Now, finally, also 50% roughly of the regular type 2 supernova show what's called flash spectroscopy features. So these are narrow lines of highly excited and ionized species, which appear during the first few days after the explosion and then disappear. Again, the most likely explanation is the compact CSM, which is excited by the strong UV emission driven through by the shockwave that goes through the CSM. And the lines disappear after a few days because this is the time it takes the shockwave to sweep through the CSM if it extends to a few times 10 to the 14 centimeters. There was a recent very nearby supernova that was detected last year at 6 megaparsecs distance, where we had early observations from the infrared to the X-rays and early spectra. And for this particular case, we could map the density structure around the star, and it shows this enhanced high-density optically thick circumstellar medium extending to a few times 10 to the 14 centimeters, followed by the more regular low-density winds surrounding such giant stars. Now, in such cases where you have a dense CSM surrounding the envelope, as the supernova shock wave penetrates through the CSM, it is initially mediated by radiation, so that the acceleration of the plasma is through inelastic component scattering of the electrons, because the energy density behind the shock wave is dominated by radiation. But as the shock wave propagates through this shell and the optical depth decreases, the photons escape, they can no longer accelerate the plasma, and the shock becomes collisionless. This is inevitable. And when the shock becomes collisionless, high energy particles are produced, and protons are accelerated, and presumably neutrinos will be produced by PP interactions that lead to pion production. So the neutrino energy that would come out from such an event is some fraction of the UV energy that comes out. The UV energy is the total thermal energy that is produced by the shock wave. If some 10% of the shock wave energy goes to cosmic rays, non-thermal cosmic rays, which is typically what we infer from different environments and for cosmic rays in the galaxy, then the neutrino luminosity would be a few percent of the UV luminosity, and it would last for these few days during which the shock wave propagates through this circumstellar shell. And if such circumstellar compact, optically thick shells are common around supernova explosion, supernova exploding stars, then the energy production rate of such explosions in the universe is going to be close to this 10 to the 43 ergs per cubic megaparsec per year. So this could contribute significantly to the neutrino background that we see. Now, since these objects are compact, 10 to the 14 centimeters, and they have huge UV luminosities, high energy photons above 100 GeV cannot escape because they produce pairs and they are suppressed, so this would be a gamma ray hidden source. This is all good. The challenge is that the rate at which supernova, which are close enough to produce more than one muon-induced neutrino-induced muon in a kilometer-scale detector like IceCube, is 1 per decade. So it's a bit challenging. But as IceCube is being increased to 10 square kilometer scale, we should be able to see these like once per year and test this theory. Okay.
So Eli, you refer to this as the CSM, circumstellar medium, that a shell surrounding this, but it could be just an extension of the star. In other words, perhaps there is some kind of a chromosphere around stars that is generic. It has nothing to do with the wind. How do we tell the difference?
The mechanism that produces these enhanced mass loss phases.
Maybe it's not mass loss.
Yeah, you're saying maybe it's still confined to the star.
Yeah.
Maybe. I think that we don't know the answer to this. We don't know what the density distribution exactly is and how it is formed. And for those who were in the previous talk about ultrasat, they know how we will be able to measure this in the future and probably tell the difference and determine the structure and maybe get a handle on the structure. I should say that I mean these models that the models that produce such extended shells around stars with energy deposition in the envelope and so on, they are not steady state models. It's not a hydrostatic steady state envelope. It's a wind that leaves the star. I'm not saying that it's not possible to create another structure, but all the models that are out there are not steady state models.
Well, models are reflecting the imagination of theories. They don't necessarily reflect reality.
That's true. Yeah.
Yeah, please, Mark.
So in those similar sort of steep density gradient models where you have some steep transition near the star towards lower density, does the shock acceleration as it runs through a steeper than, say, r⁻² profile matter a lot in terms of the production that you might get? What if you tend to have very high densities close to the star and much lower densities further out? How would that change?
You mean like this?
Yeah, exactly.
So this is the scenario that we are considering. We are considering some dense shell out to 10 to the 15 centimeters with a rapid drop afterwards.
Exactly.
So the neutrinos are produced within this dense shell with some extended mass distribution. If near the edge of the star, for example, if the breakout is from the edge of the star, the small mass that is ahead of the breaking out shock allows the radiation to accelerate it to high velocities. You don't form a collision and shock. You really need an extended mass distribution in order to form a collision and shock.
Okay. Okay.
Yeah.
Thank you.
Any other comments? Oh, please.
Very interesting. If I speak with people who model winds from massive stars, Alex de Groot, Fink, Sander, and Heidelberg, they tell me that these winds are time varying, and hence what you get is a succession of shells that intersect, and so you get density fluctuations. Is this something you could see in your time curves? Could this be a way to constrain the wind model from the stellar envelope model?
These varying winds are on timescales much longer than we are discussing. So this extent of 10 to the 14 centimeters, this is mass that was ejected during the last year before the explosion. Okay, so it's very different than these thousands of years variations of the wind at much larger scales. Now, the longer term light curve of the supernovae, okay, some try to find signatures for this varying wind in the interacting supernova. But this is all gone in the first 2-3 days. So we have so far we have very few observations of this very early timescale. We will have many more observations in the coming years to constrain this, but usually you don't see this part of the explosion because you don't detect it early enough.
Oh, yes, John.
About the X-ray luminosity,
Yeah.
would this be the synchrotron region for the electrons after the system passes threshold of 10 to 14 centimeters? Can you predict that?
Yeah, we can and we did. So the question was about the X-ray. So when the shock transitions from being radiation mediated to collisionness, the high energy electrons would also produce X-rays. Now, the transition is not immediate because initially this plasma is immersed in a very strong radiation field, and the electrons do not reach the highest energies that you need in order to emit in the X-rays. So after a few breakout times, if the breakout is at 1 day, so it's after 3 breakout times, let's say, then strong X-ray should appear. So yes, measurement of X-rays a few days after would constrain this scenario. Again, for most cases, we don't have fairly early X-ray measurements to test this.
Let's thank Eli again.
Can I start soon?
Please.
Oh, okay. So hi everyone, I'm Keiya Hirashima. I come from University of Tokyo, Japan, but currently I'm staying in CCA, Flatiron Institute. And so I'm going to talk about the AI surrogate model, which is machine learning techniques to reconstruct the simulation result. And then we are trying to apply those machine learning model to the high resolution simulations. So star by star means simulations that can handle the individual stars in the simulation, especially like in the galaxies. Oh. Okay. So before going to the simulations or machine learning side, I briefly talk about the like background of the simulations. So we want to look at the gas dynamics in the galaxies for like studying the galactic evolutions. And yeah, apparently in the galaxies, there are multi-scale gas dynamics. And for example, the most stars in the galaxies are born in the star-forming regions, which is very cold and dense. And then some of massive stars are going to explode as a supernovae, and that creates very hot gas. And also, these supernovae are releasing some chemical elements, and by their massive energy and momentum drives the outflow and the turbulence. And those turbulence can be generating next generation star formation region eventually. So that's why we care about supernovae in the galaxy simulations or galactic evolutions. So one of the challenges in such kind of simulation is the multi-scalability in simulations. So for example, when you want to study the dynamics of the galaxy, you might have to run the simulation over 100 mega years. And at the same time, to follow the dynamics of the supernovae, you have to resolve the 1,000 or 100 years in the simulations. So that makes much more time steps or calculation steps in the simulations. So it's really hard to solve both analytically and numerically. So here's the idea of our simulations. So most of the region in the galaxies are calculated with the like CPU cores. So these are just conventional direct simulations. And then every time supernova happens in dense regions, ambient gas around the supernova are going to other calculation node. And then this, like the calculation nodes specialized for machine learning techniques are handling such particles. So given the ambient gas distribution, then the machine learning model will predict the distribution of gas and the temperature and the three-dimensional velocity 0.1 mega-year after the explosion. And then the whole galaxy also advanced 0.1 mega-year. Those predicted particles is coming back to the whole galaxy simulations. So that's the idea, to decrease the whole number, total number of calculation steps. And then we fix the time step relatively longer than the required time steps to resolve the supernova usually. And the machine learning model we use is called UNet, which consists of convolutional neural networks. And the convolutional neural networks, or UNet, was invented to handle the images. And the UNet is, in the original their works, given the observational data of bio cells, and then the machine learning model will paint those pixels depending on the cells, depending on the bionic cells. So, and these are supervised machine learning. And in our case, I increased the internal dimensionality of the machine learning UNet, so from 2D to 3D. And then given the ambient gas at t equals 0, and then the machine learning, I trained the model with the the distribution of physical quantities at t equals 0.1 mega-year after the explosion. So, and the training data set is such kind of supernova explosion in the molecular cloud. So the initial temperature is 10 Kelvin, and the mean ambient density is a little bit higher than the star formation. So so since I'm mimicking the star formation regions, the ambient density is like this, and the mass resolution is 1 solar mass, which usually considered to be so this resolution can resolve the blast waves from supernovae. But machine learning model still hard to handle such large number of particles. So for only the purpose of machine learning, I interpolated those particles in the mesh data. And the calculation box is 60 per sec. So that's the, so here's prediction result. So the upper lines are input, and the second line is a ground truth, which is generated by simulations. And the third line is a prediction by machine learning model. So I don't have time to walk through everything, but if you look at the temperature, you see this inhomogeneous, the shells of supernovae. And then machine learning model can also reconstruct such inhomogeneous shapes. This is just because on the left-hand side of the explosion, the explosion is always happening at the center. And then there is a dense gas filament, so the supernova shells cannot expand on the left in this case. So the shell is just going to expand on the right-hand side. And then the upper lines are just direct simulations, and the lower ones are machine learning model, the simulation with the prediction by machine learning model. So the second columns are the snapshot just replaced with prediction by machine learning model. And then if we restart the calculation from here, the supernova shells is also expanding stably. And these inhomogeneous shells are almost similar to the direct simulations. I also evaluated this method using like conservation of temperature or the momentum, but please look at this paper if you are interested in. And finally, I implemented this like surrogate modeling for supernovae in galaxy simulations. So as a test case, I used dwarf galaxies. So this is still feasible to be calculated using direct simulations. So I compared the machine learning version with direct simulations. And in the direct simulations, the time step is variable, but the machine learning version, it has fixed time steps. So I'm not going to ask you guys to like guess which is which, but simulation, like direct simulation is the left, and simulation with the reconstructed supernovae on the left. So by human eyes, those like super bubbles are very similar, and yes. So by the way, this is like projected density distribution on the So for the validation, first I check the like speed up, of course. So if we use the surrogate modeling, we can gain like 4 times faster in the total simulations. And also in the physically, we checked the star formation rate. So it's pretty like consistent to each other. So and also we like I have to note like even though we used like exactly same initial conditions, there are still randomness in the star formation model. So it doesn't have to be like perfectly matched. So so this is like relatively very close. And also we also check the like outflow, mass outflow and the energy outflow. And so this result is also consistent to the previous simulation, but this is including like photoionization rate. So photoionization in the stereo feedback. So mass outflows are consistent, but our result doesn't have a similar values in the energy outflows. So here's a summary on the future work, and near or like the current next step, we are running the simulation with larger galaxies. So ultimately we are planning to run the simulation with Milky Way sized galaxies with 1 solar mass to 10 solar mass resolutions. Okay, thank you so much.
So Keiya, you mentioned one specific astrophysical problem, which is the supernova, that you can produce a shortcut where machine learning helps.
Yeah.
But this is just an example. Of course, you can find other aspects of any numerical simulations where you can also do the same. So what made you choose just this problem, or do you think of any other context where it would be important?
So in this context of galactic evolution, the supernova is like very impactful, and also the bottleneck of the calculations. And the effect is like locally in the very beginning of the explosion. So it's a good use case of machine learning.
But you're thinking about other applications?
So yeah, so far I planning to like think about the AGN feedback in the cosmological simulations. So it's also similar effect.
That's really impressive, and I think on the first or second slide you showed that there's a lot of very different timescales involved. And supernova is very short compared to the galactic rotation. And so it looks to me, if I understood what you said, that you kind of do this for a very short period of time and then go back to the regular simulation. So how do you decide how short, how long, like what's safe? Did you do experiments?
Yes. Yeah, this is also the result of the experiments, and the time window to skip the calculation is the 0.1 mega years. The number came from the free fall time of the molecular gas cloud, and the 2,000 years for the fixed time step came from the CFL condition. It's I guess it's corresponding to 1 million Kelvin or quarter than one. So I just forgot about the exact number, but anyway, that's the temperature of the prediction used 0.1 mega year after. So that's but it's also. Thank you.
Just a quick clarification question. So I didn't understand the architecture of your UNet. You feed it a cube of a single field at timestamp I, and then it outputs the cube of the same field at I plus 1?
Yes.
Okay.
No, not plus 1. I skipped maybe 100 steps, but I can also do such setup.
So you train a UNet for all the fields that you care about?
Yes, yes.
Okay, there were two hands. Okay, you first.
Very interesting, but there is a comparison between the simulation and the machine learning predict simulation. And if you look at the evolution, you will find the bubbles will grow at different places and if you use different recipes. My question is that we know that the machine will not give you exactly what you expect from simulation,
Yes.
but we can, from the real simulation, we can control the uncertainty from the math we use or the recipe of physics we put in. But from machine one, how could we control this kind of uncertainty, especially the bubble might be different in the machine learning simulation, but we would expect it at some specific places. So how do you control this kind of uncertainty?
So in a setup, our supernova is also happening in the center of the box because so in the simulation, we already know when supernova happens and which stars are going to explode in the next steps. So if we get such signal from the star, we make this kind of cutoff in the simulations, and then only so every time the supernova happens in the center in the machine learning model, and in terms of mass, so given this prediction, we sample the particles from the density maps because we are running the particle-based simulations. So in that sense, if we sample the exact same number of particles in the input, the mass also conserved after the prediction. Does it make sense? Or we can chat later.
Yeah, that's very interesting. So is it possible to use this model in low resolution simulation that does not result in zero stars? Essentially to use machine learning to paint feedback as if it were with
Right. Yeah, that's a good question, and that's I think the most useful case. And the answer is if it's relatively close to the training dataset, it can be implemented. But so in the axis simulation, it has 4 solar mass, and this training dataset has 1 solar mass resolution. So that's why it works. But if I choose for example 40, 50 solar mass, then we cannot make this kind of maps because the particles inside the box is too small number. So I need such optimization still if I want to use this model in the low resolution simulations.
Okay, let's thank Keiya again.
Thank you so much.
Hello, I'm Yijia. I'm a PhD student from Penn State working with Yijia, and thanks for having me here. I will be talking about our new flexible emulator of the photonization code, Cloudy, and it's a very flexible emulator that can fit almost any ionizing source if it's the machine learning theme today. And as seen by JWST, we find many high redshift galaxies show very strong nebular emissions, and some of these galaxies have very extreme ionizing condition that we've never seen in the local universe. And in the left plot, you can see that compared to local SDSS galaxies in the blue, these normal star-forming galaxies at high redshift show potentially higher ionization condition, and also they show low metallicity and high gas density. And it's very important to understand the nebular emission of these galaxies, but the low dimensional model we've been using is not sufficient for these complicated cases. And furthermore, JWT have seen some galaxies with very strange abundance patterns, and in the left is the famous galaxy GNZ11, and we can see from the emission lines that it has a very strong nitrogen enhancement. And in the right, there are more galaxies seen by JWT that with nitrogen and hydrocarbon enhancement. And so there must be some process to release the carbon and nitrogen formed in the CNO cycle to the ISM, and some potential solution includes AGN's Wolf-Rayet stars dynamical effects in dense environments. And so what could be the ionizing sources of those extreme galaxies? And one common way we've been using to diagnose the source is through the line diagnostic plot, such as BPT diagram. But the line diagnostics calibrated at low redshift may not work well for those high redshift galaxies. And here is the Ono diagonal, and which I like the name. So as you can see, many high redshift galaxies locate in the composite region of the stellar and AGN region in this diagnostic plot. And more importantly, there are other sources we haven't thought of at low redshift. For example, surprisingly low metallicity OMB stars, stellar populations with top-heavy IMF, POP3 stars, etc. So that's the motivation why we want to build a more flexible emulator for the nebular emission modeling. That's why we built Q, and Q is a neural net emulator on Cloudy. So usually how a photonization code like Cloudy works is it includes three components: the ionizing source, the chemical composition of the gas cloud, and the structure of the gas cloud. And one key feature of Q is that it's source agnostic. So by approximating the ionizing spectrum with a 4-piecewise power law instead of assuming some star templates or AGN templates, we can fit to any sources with a continuous ionizing spectrum. And also by directly infer the ionizing spectrum, we can maybe learn what the source is. So QP can be used as a discovery tool. Also, we allow large freedom in ionization parameter, gas density, gas phase metallicity, and N2O and C2O ratio. So this is a demo of one of our fit, and it's a fit to near spec spectrum of a redshift 2 galaxy. And in the left is our ionizing spectrum, our 4-piecewise ionizing spectrum and the nebular properties, and in the right is the predicted emission lines. And Q can predict over 100 UV to sub-millimeter emission lines and nebular continuum within 5% uncertainty. and it's also very fast. So each prediction takes less than 6 milliseconds. So that's a 10 to 4 times speed up compared to cloudy. And our mock tests show that we can produce useful constraints on the ionizing spectrum with 5 to 7 lines at signal-to-noise ratio greater than 10. But if we only have low signal-to-noise ratio lines, we won't be able to constrain the ionizing spectrum and nebular properties. So as I've noted, Q can be used as a discovery tool for the ionizing sources. And to make this more clear, here we show the ionizing spectrum of different stellar models and different sources. And the range of Q is marked in black lines, so it's designed to enclose all these ionizing sources. And in the left, you can see that BPAS stellar model predicts more ionizing photons than the single stellar evolution model Padova, because BPAS can prolong the lifetime of the massive stars through binary evolution. And also in the right, you can see that AGNs and post-AGBs produce a harder ionizing spectrum. So in principle, if we can have a tight constraint on the ionizing spectrum, we might be able to tell what the source is. And also there's some large systematic uncertainty in the SED modeling of galaxies for those emission lines, because the ionizing spectrum of the massive stars are highly uncertain, as their evolution paths and mass loss rates are uncertain. So by directly infer their ionizing spectrum, we might be able to interrogate the stellar models we used in SED fitting. So how's the performance of Q in real high redshift extreme galaxies? Here as a showcase, we fit a nebular galaxy at redshift 6 with Q. And this galaxy have very strong Balmer jump and also strong Lyman emission with UV turnover. So the only two ways to make the Lyman emission and the UV turnover is through the nebular continuum or a very strong damp Lyman alpha absorber. So if we believe it's the nebular continuum powering the UV turnover, then as suggested by Cameron and Hatz, we need to have a very top-heavy IMF, or essentially a top-only IMF solution. But is there another explanation? So we fit the emission lines of this galaxy with Q, and Q has a good fit to the emission lines comparable to the top-heavy IMF solution. And our fit infers that the nebular continuum only contributes about 30% of the flux in the UV. And we further decompose the ionizing spectrum with a stellar population and an AGN, and we find that the ionizing spectrum can be explained by young low metallicity stars and an AGN. And also as an ongoing work, we are applying Q to the Blue Jay survey. Blue Jay is a cycle 1 year spec program on a massive lattice sample of galaxies around redshift 2. It has 3 out of 1,000 gratings, and there are many people here also in the Blue Jay team, like Ben Johnson, MJ Park, Charlie Conrad, and Racy, Emma Mead, Malbody. And here we show the spectrum of a star-forming galaxy and a quiescent galaxy from Blue Jay. So you can see from this beautiful spectrum, we can constrain the ionizing properties from the emission line properties and constrain the stellar populations from the absorption features. Here is what we are doing, just to be more specific. So we feed the stellar continuum of the blue J galaxies with prospector and infer the stellar populations, and we feed the emission lights with Q and get the infer the ionizing spectrum, and we compare those two and see what if our ionizing spectrum agree with the young stars from the SED modeling. And as a preliminary results, we select a subsample of low mass dust-free galaxies, and our inferred total ionizing spectrum output of those sample is consistent with BPAS, but the shape of the ionizing spectrum is very different, and about 6% of our sample has a much harder ionizing spectrum than the young stars from the SED fitting. So we might think the stellar models might need to include some extreme star models like strip stars. So that's the summary. Thanks. Yeah.
We're a little bit short on time, but we'll take a question if there is any. Yeah. Right.
This is very interesting. I think it has been long proposed to use machine learning tools as interpolators or extrapolators to all these emission line diagnostic tools. As I understand, and from our own work in Heidelberg, the culprit often is or the thing that makes the prediction very difficult is the handling of dust and extinction and reddening in the galaxy or on a stellar scale. So I was wondering how you deal with that uncertainty. Is this a feature that you also include in your modeling?
In our galaxy Celeste sample, we intentionally select the dust-free galaxy, so we don't need to care about the dust attenuation. But in our model, Nebular model, we include some dust depletion factor, but we don't account for the dust within the H2 region. So that's some next steps we want to include. Yeah.
Which I think makes your prediction much more complicated and much more degenerate.
Yeah. Yes. Yeah. I agree. Yeah.
We need to move on, so let's thank
Thank you.
Yijia.
Hi everyone, I'm Michelle. I'm currently a postdoc in Karin's astrochemistry group, and I will not be talking about machine learning today. I've been doing some laboratory astrophysics experiments, and we're looking at methyl cyanide and how it can be stable as well as react with other molecules and ices to simulate conditions that we would see in dust grains. And so over the course of a lifetime, from a cloud all the way to a protoplanetary disk and then a planetary system, we can have ices and molecules that are incorporated in throughout this environment. And so our goal is to really look at the very ancient part of the ices and the beginning part of the molecular cloud and try to understand the abundance of these molecules and then how they can then remain stable and then change over the course of this process. And so to do that, we're focusing on the very beginning part. These ice grains that are in these molecular clouds are very dynamic processes. And so the ice can be bombarded by a variety of different methods, whether that's hitting from a cosmic ray, being hit by an X-ray or an electron. And what happens is that from that bombardment, you can then produce radical chemistry that occurs in the grains. And so the radicals that are nearby with different neighbors can then combine together, and either molecules can be destroyed or they can then form more abundant molecules. And so there are molecules that can be produced both in the ice grains as well as in the gas phase in these types of molecular cloud environments. But the reality is that some of the more complex molecules, meaning methanol, for instance, are really formed specifically on the ices. And so that's why we're really focused on ice grain chemistry here. And then this is an example shown on the right. What we can see is that these more complex molecules can be detected in molecular clouds, ranging up to molecules that are containing not only oxygen, but then also nitrogen-containing molecules as well. And so specifically in these ice grain environments, when the ices are really cold, it's possible that if a radiation hits the ice, it can then form radicals. But if those radicals are then frozen, they might not be able to react or then combine to form new molecules. So in that scenario, you can have oxygen addition reactions that could be a pathway to form these more complex molecules instead. So in this scenario, you have an ice, a grain. It's composed of some reactants combined with either ozone, molecular oxygen, carbon dioxide. And when the UV hits the ice, it can then break apart the oxygen to then form excited state oxygen atoms. So that's what I'm showing on the right. And then that excited state oxygen atom can then insert into, let's say, methane or other types of hydrocarbons to then form alcohols such as methanol. And so the project that I've been focusing on recently in the lab is using methyl cyanide, and we're asking the question, can you do the same sort of insertion chemistry that you would see with methane to form methanol, but with instead with methyl cyanide. And so that's what I'm showing here on the bottom. So methyl cyanide, for those that aren't familiar, has 2 carbons and then also has a nitrogen. And these experiments were all done in the basement of the P building. So for those that are local and want to see a tour of the lab or haven't been there, feel free to let me know. I'm happy to show you around. But this is a picture of the experimental setup. The chamber is at very low pressure and low temperature, so we're about 10 to the minus 10 torr, excuse me, and about 10 Kelvin. And over the course of the experiment, these experiments can happen on the lifetime of about a day, so work in the lab for one experiment. What I'm doing is I'm introducing gases first into the chamber. So those gases, in my case, it's methyl cyanide and oxygen. They're introduced into the system. They're deposited onto a very cold substrate, frozen in place. And then I'm using infrared spectroscopy to monitor both the molecules, the abundances, and then look at how those molecules are interacting with other molecules. And then over the course of the experiment, I'm then hitting it with lots of UV photons. So I'm using a UV lamp that's on the back of the setup here. So I'm doing this over the course of hours, simulating like 10 to the 18 photons. And then I'm continuously throughout this process taking infrared spectra and then monitoring exactly what's happening to these ices, how they're interacting with the UV, and the stability of the molecules over time. And at the end of an experiment, so I've done this for multiple hours, I anneal up the surface, so I'm doing what's called temperature programmed absorption. And then I can monitor not only the infrared spectra of what's still on the surface as the temperature is increasing, but also get molecular identification for molecules that are entering the gas phase and then being detected by a mass spec, quadrupole mass spectrometer. And so this is just an example of one molecule. I annealed it up from about 40 Kelvin to 200 Kelvin. In this annealing process, we do it over the course of about an hour or two, so that way we can get nicely resolved mass spectra. And so I've deposited my ice. I have a mixture of methyl cyanide with oxygen, and I've bombarded it with these UV photons for many hours. And the first thing I just want to note is that The methyl cyanide before the reaction is in orange, and the gray is afterwards. And so the first thing that you can see, I'm not going to identify all these peaks, it's not necessary here, is that the methyl cyanide reacts very quickly, and that we're producing a lot of products from this reaction. So methyl cyanide is not very stable to UV photons. And what I can do is I can integrate, so I can take a spectra and then calculate the number of layers or the number of molecules, and then I can calculate that as a function of all the exposure of the course of the experiment. And that's what I'm plotting here on the right. So we have the beginning part, we have more methyl cyanide, and then over the course of the experiment, as I'm bombarding it with the UV, we see the destruction of the molecule. And the gray point at the end is just that last spectra that I've showed you on the left. And so this molecule really readily reacts. We're forming all these products. And one of the products that is of particular interest that we've been able to identify so far is methyl isocyanate. And I've put a spectra down in the corner here for those that are less familiar. And this zoomed in image is really just showing the same spectra. We have the 3 peaks in the carbon-nitrogen region. And we can see that over the course of the experiment, we start out with none, which makes sense. We only have our methyl cyanide and our oxygen mixture. And then over the course of the experiment, we're growing in a little bit of this product. And this is an interesting product just because it is showing oxygen incorporation into our molecule and then still containing one of those nitrogen atoms as well. And so in addition to doing this experiment where I had methyl cyanide and oxygen, I also did a complementary experiment where I did oxygen, but I isotopically labeled it. And so I have the same experiment on the left, and then I did experiment with oxygen 18. And what I'm showing here is the temperature per-gram desorption. So again, it's the masses as I'm annealing it off the surface. And what we see is that there is a 2 mass number shift corresponding to the oxygen labeling. And the desorption temperature that we're seeing is corresponding to a temperature at which I no longer see the methyl isocyanate in the infrared spectra, and that is also matching some other previous literature studies. So this is helping to confirm that, yes, we're producing one of these products, and that we're producing one of these products and we can identify it both from the infrared spectra, so what's on the surface, as well as what's desorbing off the surface as well. However, when I ran these experiments, if I just go back for a second, we're really not producing that much of this methyl isocyanate because one of the reasons is that the methyl cyanide is just really reactive with those UV photons. So I've been working in collaboration with the lab manager to do some infrastructure upgrades to the lab to implement an ozone source. And so that's what this looks like right here. It's exactly what it sounds like. It's an ozone generator. And so we're producing ozone. Ozone is O3 for reference. And then as of last week, we've been able to produce the ozone, incorporate it into the system the same way that I would deposit the molecular oxygen. And this is just a spectra showing, yes, we produce ozone, great. And what we've done is we've switched out our lamp. So now we're in a regime, we have a new UV source, and we're gonna be able to run experiments over the next week or a couple weeks to then look at breaking apart that ozone to form oxygen atoms without breaking apart our methyl cyanide. So I'm excited about that. Stay tuned, hopefully I'll be able to share more about that in the future. And since it beeped, I'll just leave you with my conclusions.
So Michelle, should we be worried that there is cyanide produced in the basement? Is there any health risk?
So I would say our system is very much enclosed. So if I just go back to our chamber environment here, there's no scenario where any of the cyanide that would be produced is ending up in the atmosphere near where I am. And also for the ozone source, we have a lot of additional safety precautions. So I have It's like a little field ozone carrier that I can like clip onto my belt, and then I can measure to be like, just make sure that the ozone's not leaking out. And I also leak checked it for at least a whole week to double check that. So trying not to be in an unsafe environment, yeah.
Any comment, question? Everything was clear. Let's thank all our speakers today.